Today in class we talked about Le Chatelier's principle. We talked about how changes in concentration and changes in pressure can shift that equilibrium to the left or the right depending. One thing that we do need to address though, and we didn't address it today, that if we have changes in concentration and pressure and we do shift that equilibrium, we do not change the equilibrium constant value k. It doesn't change it. It just shifts the equilibrium one way or another. But the last of the stresses, according to Le Chatelier's principle, is the stress of temperature change. Now, we do need to remember that temperature can change the equilibrium value, and we'll get to that later on. But let's keep that in mind. So let's go do a quick little review of something we talked about a while ago when we talked about thermochemistry and thermodynamics. Remember, if we have an exothermic reaction, exothermic reactions are going to be reactions where the delta H is a negative value, often given as like delta H is equal to negative 890 kilojoules measure of heat. So if you have that as a negative value, we know that you have an exothermic reaction. It's a reaction that's going to be giving off heat to the environment. We can also look at thermochemical equations that have reactants listed on the left and products listed on the right. And then we have heat also listed as a product because heat is being given off in an exothermic reaction. Now, in an endothermic reaction, endothermic reactions are going to be reactions that absorb heat. Delta H value is going to be positive. We would write a thermochemical equation as reactants plus heat yields products. Sometimes they just write the word heat, other times they will actually give you the measurement of 810 kilojoules actually included into the equation. And the trick behind predicting a shift in an equilibrium is to treat heat as it is just another reactant or product to predict the shift. So let's get down to an example where we can do this, and I'm going to walk you through this now. Now, if you would like to pause the video now and work these by yourself, that would be a good thing to do. Or you can just follow along with me while we do this together. Okay? So, let's take a look at this. So we have an equilibrium of N2O4 and we have 2NO2, they're both gases. We have a delta H value given as 58.0, which lets us know that this is an endothermic reaction. Endothermic reaction. And so if we were to include this, we would include it on the reactant side. So it would be 58.0 kilojoules over here because we include endothermic reactions on the reactant side. So if we're going to predict the shift, some of these are things we talked about in class today. So if we were adding NO2 to this equilibrium, well, because NO2 is a product, we would have a left shift, and the N2O4 would be increasing in concentration, the NO2 would be being added. N2O4 is being removed. Remember, if you add something, it shifts away. If you remove something, it shifts toward. So it's going to also be a left shift. Pressure is increased. Remember when we dealt with pressure, always shifts to the increases in pressure shift to the least number of gas moles. And so in this balanced equation, we have 2 gas moles as a product. We have 1 gas mole as a reactant. So increasing pressure is going to cause a left shift as well. Now we get down to the heat, which is what we were talking about today. So heat is added. Now what we're going to do is, because we wrote heat on the product side, heat was written on the product side because it was an endothermic reaction, we're just going to treat it like it is another reactant. So if we were adding a reactant here, we would be shifting away from that. So the system will shift to the right, producing more NO2 and reducing the amount of N2O4. Now, if the system is cooled, again, this is the same exact system. So instead of adding heat, we're removing heat. Okay, so the system is cooled. So like I said, instead of adding heat, we're removing heat. So if we added heat, it does shift to the right, as in the example in D. So we're cooling it, it's going to shift left. Okay. And the last one we're talking about here is if the volume of the container is increased. Now remember, there is an indirect there's an indirect relationship between pressure and volume, and meaning that when volume is increased, then pressure is going to decrease. So if we decrease pressure, what's going to happen? It's going to shift to the side with a greater number of moles, and the greater number of moles was our product side. We're going to shift right. Okay, and that is our last of the three stresses that we're going to talk about for Le Chatelier's principle, and so there will be some practice problems that go along with this.